Hello everyone and welcome to the MathDBase.com Anacast series. I'm your host, John Kisiedu. In this installment in the Developmental Mathematics series, I'm going to discuss the decimal system, Part 1, Numbers in Common Usage. The value of a specific digit in a number is determined by its position, called its place value. The smallest value of a whole number is that of units or ones, the next is tens, and the next position is hundreds. Each position in a place value chart is 10 times as large as the place to its immediate right. Numbers grow in value from right to left and are read from left to right. In the number 2131, the first digit 1 represents a single unit, 1 of something. The second digit 3 represents 3 tens or 31s. The third digit, another 1, represents 10 tens or 100 ones. The last digit 2 represents 20 hundreds, 200 tens, or 2,000 ones. The three basic positions in a place value chart, units, tens, and hundreds, are called orders. A group of 3 orders is called a period. The first 5 periods in order of increasing value are units, thousands, millions, billions, and trillions. Each period contains a units, tens, and hundreds order. In written numbers, periods are separated by commas so that when looked at from right to left, will be a comma after every third digit. In most European countries, periods are used instead of commas to separate the numerical periods. For example, the 3, 0, and 6 of the thousands period in this place value chart represent 6 thousands, 0 ten thousands, and 3 hundred thousands respectively. The 7, 3, and 5 of the billions period represent 5 billions, 3 ten billions, and 700 billions. To read a number, we start at the largest period and work our way through the periods and orders from left to right. So the number at the bottom of this place value chart is read 735,829,306,713. A digit such as 3 can represent different values depending on context. For example, in the number 53,415, the 3 represents 3,000. The 3 in 637,271 represents 30,000s or 3 ten-thousands. The 3 in 13,025,001 represents 3 millions, and the 3 in 7,342,669,451 represents 300 millions. If we are given the digits 3, 9, 6, 2, 7, 9, 1, and 5, and asked to write the smallest possible number using only these 8 digits once, we have to make sure that the digits from higher periods and orders are smaller than those from lower periods and orders. With 8 digits, we can form a number in the tens of millions. Choose 1 as the value of the tens of millions place, 2 in the millions, 3 in the hundred thousands, and so on, until we get to the units place. So the smallest possible number from these 8 digits, if each is used only one time, is 12,356,799. To find the largest possible number, we reverse the process and make sure that the digits from higher periods and orders are larger than those from lower periods and orders. We would have 99,765,321. If the first 9 is replaced with a 0, then the largest number that can be formed would only be in millions, not tens of millions, since a 0 in the tens of millions place does not increase or decrease the value of the number. That 0 acts as a placeholder, indicating that the value of the 10 millions place is 0. Since zeros at the left of a number do not contribute to its value, you can think of any number as having an uncountable string of zeros at the beginning, indicating that all of those places have values of 0, though those zeros are usually left off. Exponential notation is the use of exponents as shorthand in writing large or small numbers. In the expression a 10 with a small 3 above and to the right of it, pronounced 10 cubed or 10 to the third, the 10 is called the base and the 3 is called the exponent or power. The base tells you which number to repeat and the exponent tells you how many times to repeat it. 10 cubed is the same as 10 times 10 times 10, which equals 1,000. Similarly, 3 to the fourth is the same as 3 times 3 times 3 times 3, and is equal to 81. 10 to the 7th is a shorthand numerical way of writing 10 millions, a 1 followed by 7 zeros. Numbers in the hundreds, thousands, 10,000s, and 100,000s occur in the average person's daily life, such as in the number of students in a school, the price of a house, or the number of miles on an old car's odometer. Millions occur in the average salaries of star athletes or in the distances in miles from the Earth to the Sun or other planets, and the number of seconds in a year. Numbers in the billions are commonly spoken of when referring to the revenues of large businesses in billions of dollars. The current maximum capacity of an average personal computer hard disk in gigabytes, or the number of chemical base pairs that comprise human DNA. Numbers in the trillions are common when referring to the gross national product, GNP, which is the total value of all goods and services produced over a year of highly industrialized countries such as the United States, Germany, and Japan. Numbers beyond trillions are typically only encountered in mathematics and science. 10 to the 20th is the probable range of the number of grains of sand on a typical beach. Governments, large businesses, and banks use numbers in the 10 to the 199 range for public key encryption codes in electronic communication. By contrast, the number of electrons in the universe is once stated to only be in the 10 to the 82 range. It is interesting to note that the system for naming the periods in the United States is in agreement with that used by much of the rest of the world only through millions. Both systems are of French origin, but the French themselves use the system that is used in the United States and modern Britain only until the 1940s. The US system uses the familiar period names in progressions of thousands, 3 zeros, whereas the European system uses them instead for millions, 6 zeros. The Ilian suffix suggests 6 zeros in the European system and uses Latin and French prefixes to form the names. After million, there is bi-Ilian, or billion, 2 sets of 6 zeros, or 12, then tri-Ilian, or trillion, 3 sets of 6 zeros, or 18, vigintillion, 20 sets of 6 zeros, or 120, through centillion, 100 sets of 6 zeros, or 600 and beyond. Beginning with the 4th period and progressing every other period, the European system uses the same prefixes bi, tri, quad, etc., but a completely different suffix, iliad. The term Google, not to be confused with the internet search site which has a different spelling, was coined for the number 10 to the 100, a 1 followed by 100 zeros in 1938 by the 9-year-old nephew of American mathematician Edward Kasner. In the US system, the 34th period is dotrigintillions, a 1 followed by 99 zeros, so Google's original name was 10 dotrigintillions. The number Google comes up when talking about the number of subatomic particles in the visible universe as a means of comparison.